In our previous discussion, we talked about narrowband FM and narrowband PM in the context of bandwidth of angle or exponential modulation. And it was found that for the narrowband FM, the bandwidth is actually equivalent to that of AM signals. We also compared narrowband FM with AM in terms of line spectrum and phasor diagrams previously. In today's discussion, we will deliberate on more generic aspects by relaxing the assumptions that we have previously made, and we would then discuss on the bandwidth of angle modulation. There are actually no closed form expressions which are generic. So we would be finding ways in which we can find the bandwidth of an FM modulated signal. So in our previous discussions, what we have discussed is that the modulated signal, if we have a message signal m of t, then that message signal is passed through an integrator and we get this block minus infinity to t, the integration of m of alpha d alpha, and we often call this as a of t. We multiplied with the sensitivity constant kf and then add it with the carrier frequency omega ct, right? So this is our FM modulated signal. So in the previous class we mentioned that if this whole thing kf multiplied by a of t, if it is much smaller, so if it is much smaller, then this component would not play a very significant role in the perturbation of omega ct. This value would be very small. So whether we are having a positive value or a negative value, so we would not be adding a lot to it, or we would not be subtracting a lot from the carrier frequency. So in that case we have a narrowband FM, right? So by the way, just on a side note, if you are going to take the power of this modulated signal, so anything which is inside the argument, so if this is a cos function and then inside the argument, if you are going to take the power of this one, so it will become, so let me just write it here. So if we want to find the power of GFM of t, the average power, so that would be equivalent to a square cos square, and just let me call it theta dt, right? So this whole thing would be the cos square theta is 1 by 2 plus 1 by 2 cos 2 theta, so this would become a square by 2 plus 1 by 2 cos 2 theta d, so d theta. So this whole thing is basically in terms of cos function, so it's oscillating at double the frequency as compared to the original argument, but anyways our upper sideband would cancel with the lower sideband and this whole thing would become 0. So eventually the power is just a square by 2. So over here the power is simply a square by 2. So the question is, what if this condition is not met? If this condition is not met, then the bandwidth of FM would be greater than the bandwidth of AM, or it would be greater than if the bandwidth of message signal is simply BM. For narrowband FM, so bandwidth is approximately equal to 2 BM. But if this condition is not met, then we have wideband FM, which is definitely greater than 2 BM, and at times it's much greater. So we will deliberate on this point further on. In order to determine the exact bandwidth, we have to adopt certain procedures, and then based on those procedures we would eventually get the bandwidth. As a first step, we approximate the signal GFM of t by another signal that results from modulating a sampled version of the message signal. So by this what I mean is that if I have a message signal, For simplicity, I'm just considering one single tone message signal. So this is our m of t. So there is no closed form expression by means of which we can determine the bandwidth of this one, the message signal when we modulate it and we get GFM of t. So in order to modulate this, we follow a process which we call as sample and hold. So we will pick this sample and we will hold it for some time, and then we will pick this sample and hold it, then pick this sample and hold it, and so on. So this is technique is called sample and hold. It is also called first order hold. So this staircase signal, we can just simply call it as m hat of t, and we can approximate whole of this signal on the left side and on the right side by m hat of t. So if we consider this message signal and if we modulate the m hat of t, we would get GFM hat of t, and we would claim that the bandwidth of this one would be equal to the bandwidth of a FM modulated signal based on m of t. So that is basically the forthcoming discussion. So let us start with a more clear picture. Over here, the blue line, this single tone, is basically our message signal, and the red one is sample and hold. So we pick a sample and we hold it for a certain time. The duration of the time is expressed in terms of delta t. Now to understand what is the range of delta t, we have to follow a Nyquist sampling theorem. And why is it so? It says that in a time domain signal, if you sample a signal fs, let me call it fs, if you sample a signal which is greater than or equal to 2 times the maximum bandwidth of a message signal bm, right? So in that way you would not lose any information. You can recreate the original signal. So if I interpret it in terms of a block diagram, so the system which is a sampler, if there is an input x of t and then there is x hat of t, so this system, if it is following this criteria, the Nyquist criteria, then it is reversible. So from here you can go there, and from there you can come back to x of t, right? So this is basically governing the duration of our step in a staircase. So how long are you going to hold the sample and then pick a new value and then hold it? So based on this, we say that the delta of t is equal to 1 over 2 bm, right? It's coming from here. We can get the sampling frequency ts is equal to 1 over fs, or simply delta t is equal to 1 over fs, or is equal to 1 over 2 bm. So this is the minimum duration that you would desire. Now there are some very fundamental aspects for both the message signal m of t and the approximated m hat of t. The first and foremost, if you see, this signal has a peak value at this point. Message signal m of t has a peak at this point. Similarly, approximately at the same point, you're picking a sample and then holding it. So m hat of t has also the almost similar peak, maximum peak. Similarly, on the lower side, the negative peak, you have the message signal m of t blue one is at minus mp, right? And similarly, for the staircase one, again you have minus this whole value, this block is at minus mp. So what I'm trying to say is that for both the signals, the peak values, the minimum value and the maximum value is almost similar, right? So if they are similar, then this plays a key role in terms of modulation. Remember, the amplitude of the message signal governs the change in instantaneous frequency for FM modulation. The maximum, the amplitude of the message signal, the maximum oscillation in the modulated signal that you would have, and the minimum, the peak, the minimum oscillations in the modulated signal that you would have. To summarize this point, so we can say the message signal has peaks minus MP and MP, and similarly the approximated message signal m hat of t again has peaks minus MP and P. We can say our modulated signal is a cos omega ct plus kf, and then m of alpha, this the integration of this is over here. And similarly for gfm of gfm hat of t, the only thing is instead of m of t, now we have m hat of t, which is reproduced over here after passing through an integrator, right? So this whole thing kf into this a of t would govern the change in the carrier frequency. So this change is basically expressed over here. This we can write as kf times a of t, but this a of t is consistent for a period of time. So assuming we are considering this point until here, so for the approximated signal, the value, the amplitude is consistent, right? And that would mean that the oscillation at that particular interval is also consistent, it's not changing. But once you will get a new value at a new sample value, so since the amplitude decreases, so this value would actually decrease, and so on. At this point you would have minimum oscillations, right? At this point we have maximum oscillations. So compare it with the message signal m of t originally. So if it was original m of t without approximation, so the instantaneous frequency would keep on changing continuously, and then it would decrease as the amplitude of message signal would decrease. We are basically making blocks, and from those blocks we are determining what would be the instantaneous frequency for that particular block, right? Just to reiterate, so instead of finding the bandwidth of message signal, now we are finding the bandwidth of an approximation of the message signal. So we can say that the instantaneous frequency is basically bounded, upper bounded omega c plus kf mp, omega c plus kf mp. So mp is the peak value, so it is upper bounded by this value and lower bounded by omega c minus kf mp, which is over here, omega c minus kf mp on this point, right? And this is basically kf mp is the frequency deviation, which we call as delta omega, right? Or this is in radians per second, or simply in hertz, kf mp over 2 pi, that is delta f, right? So an interesting line, this I would like to read it, that so to approximate the bandwidth of the original FM signal, we would compute the approximate bandwidth of the approximation signal GFM of t. So there are two sets of approximations which come into play. So first of all, we are approximating the bandwidth, so it's not exact, and even that approximation is basically based on an approximation of the original message signal itself, right? So we'll be finding the spectrum, and based on that spectrum we would say that what the bandwidth of the message signal is. So considering this figure, what we would do is we will just pick one block, not all, just one. So say we are just picking this block over here, and based on the what you call the linearity property, the time domain signal is basically sum of all these samples. So if we can just express them as this signal plus this signal plus this signal and so on, so that would come from the linearity. We can just add it. So we are just taking one block at a particular time, and we are calling it by z of t, right? Now in this particular block, what we have is we have a gated cos function. So by gated, what we mean is that if you have a rectangle function, so if you make a rectangle function and then you have a sinusoid, right? So the sinusoid would only be valid until this point, and these would become zero when they will multiply with a zero over here. This is a gated cos function, right? As I mentioned, from the Nyquist criteria, the value of delta t is 1 over 2 bm. So let's talk about each block first. T by tau. This is simply, if we plot it, that is minus tau by 2 to tau by 2 in time domain, right? So what we need is we have a delta function which is 1 over 2 bm. So if it was at the origin over here, so if it was at the origin, then it would be something like this function, minus 1 over 4 bm 0 and 1 over 4 bm. So this width would be 1 over 2 bm, right? Now from here we can say that to achieve this, our value of tau is 1 over 2 bm, bandwidth of the message signal. So if you put tau is equal to 2 bm, we would achieve this rect function. But this rect function is basically shifted. We have shifted it by t naught, right? So that's why we say rect function 2 bm t minus t naught, right? And this is multiplied by a cos function. But as I mentioned that we are interested in the spectrum of this. So if we are interested in the spectrum of this, what we need is we need a Fourier transform of z of t, that is z of omega. And for that we know that if we have a rectangle function, if we take the Fourier transform of this, so we would have tau sinc function for a rectangle function, tau omega by 2, right? So this would mean that we have a sinc function in omega, and that is like that. The first lobe would have a zero crossing, the first zero crossing at 2 pi by tau. So if we set tau equal to 2b, so that would mean that this point is 4 pi b, and similarly this would be 4 pi by tau, and we can translate it to 8 pi b and so on, right? So this is in omega domain. There are several set of properties that have come into play, that includes time shifting property and frequency shifting property. So we can use the Fourier transform tables to get these values, and previously we have also covered this in one of the examples in class as well, right? So specifically I have mentioned for a simple rectangle function we have a sinc function. So for this particular gated cos function, we would have z of omega, which is centered at omega I, and the first lobe over here that would terminate at omega I plus 4 pi bm, right? So center is shifted to omega I, omega plus omega I, which is over here, omega plus omega I. So omega plus omega I is shifted towards the left side, and omega minus omega I is shifted towards the right side. So this is omega minus omega I, right? And then the next thing is this 4 pi b at the first crossing. So 4 pi b, and then it oscillates. Similarly, on the left side we have uh, omega I minus 4 pi bm. So this is a spectrum of one gated cos function, and this the oscillation, the oscillatory frequency, the frequency is basically determined using the amplitude of the message signal, which was over here. So next is, so if we have lower amplitudes like this, so the number of oscillations would decrease, and the oscillations, if they would decrease, we can follow the same principle, and that would mean that if we have this over here, if the frequency decreases, if you take uh, a lower value of the staircase, so at the peak value we have this one, and at the negative peak value we have this spectrum, right? So this dictates the overall bandwidth. Now let us deliberate on this bandwidth. Over here we have a carrier frequency omega c, we have omega c plus kfmp. So it's not clear, let me write it again, kfmp. For the negative peak, the center frequency is omega c minus kfmp, right? And then until the main lobe we have omega c plus kf, omega c kf mp plus this point, which is 4 pi bm, as we have discussed previously over here. So omega I plus 4 pi bm, so 4 pi bm. So if we need to find, if we need to detect the bandwidth of this signal, so what we would have is, we would have simply 3 blocks. So from here and here, this is the first block, and then on the right side we have a main lobe until here, and on the left side we again have a main lobe, right? So if we need to find the bandwidth, we can just simply subtract this from this, then that would give you the bandwidth at this point, from this point to this point. And this over here is omega c plus kf mp minus omega c minus minus will become plus kf mp. So this would become 2 kf mp plus this side lobe, which is 4 pi bm, plus this side lobe again, which is plus 4 pi bm. So main lobe to main lobe of the least amplitude or the negative, the minimum value of the message signal, the starting point of the main lobe, and the terminating point of the main lobe of the maximum value of message signal, right? So when they are reflected to in terms of omega, so this is our bandwidth. So from here we can say that the bandwidth is 2 kfmp plus 8 pi bm, which we have mentioned here, 2 kf multiplied by mp plus 8 pi bm. So this kfmp we can simply express it in terms of frequency deviation which is radians per second, or delta f in hertz. So this is 8 pi bm. So next, just a small simplification, delta omega mp over 2 pi, so that we get it in terms of hertz rather than radians per second. So then this would become delta f plus 4 bm, and this is equal, we can take 2 as common, so 2 delta f plus 2 bm. So based on our analysis, remember this is not a closed form expression. All of this we have just visualized. We took one sample, and from that sample we get a time domain expression, and we converted that into a Fourier transform expression z of omega, and then we said that based on the amplitude of message signal we could have different spectrums, and end-to-end value of that spectrum is the bandwidth. So this is not based on an closed form expression, but just from the visualization. So from the visualization we have expressed that the bandwidth of fm is 2 delta f plus 2 bm. An important point to note here is that we have not assumed something like kf mp, the value of that is smaller, as we have done for narrowband fm. So we have not done that here. Okay, so the interesting point, this value over here is not accurate. So all this discussion, as I mentioned, is based on visualization, and this visualization dictates that, or it shows that this expression does not actually give you the exact bandwidth. Why is it so? So as we have mentioned that this is generic, so let us test this for narrowband FM. So in narrowband FM, we say that the value of delta F is much smaller than 1, right? So if it is much smaller than 1, so that means this delta F is approximately equal to 0, and this, if this is approximately equal to 0, then for narrowband FM the bandwidth is approximately equal to, this would become 0, 4 bm, but this is an overestimate. For narrowband FM we have claimed that the bandwidth is actually 2 bm, not 4 bm. So this is a point which Carson identified, and he came up with one idea that we can correct this overestimation by just getting rid of this 2, which we have done over here. So if you get rid of this 2, we have 2 delta F plus bm. So this expression is basically termed after him and is called Carson's rule. Now if you test narrowband FM, and if you test the narrowband FM, so we say that delta F, if this is very small, approach, if it is 0, so then for that we have 2 bm, which is in agreement with narrowband FM. The Carson's rule gives you a value which is basically not overestimating, but later on we will see it has its own set of issues, but so far it is just giving us something which is not overestimating. So we can also say that the bandwidth of FM is in terms of radians per second 2 delta omega plus 2 pi bm. Another important expression which we can govern from here is that if you take bm common, so we can have 2 bm delta f by bm plus 1, right? And this thing we can express in terms of beta 2 bm, right? So this is an expression that you would come across in the textbook and in a number of places. So bandwidth of FM is 2 bm beta plus 1, where beta is the modulation index. This modulation index beta has a value of less than 0.3 for narrowband FM, but for wideband FM it has higher values.